Hello, everyone, and welcome to our great webinar. Thank you for joining us today. A small part about IPMA SIG Energy, just a few words. IPMA SIG Energy is a public group. It's a global community connecting project management professionals, industry experts, and academics to share knowledge and best practices across all sectors of energy. Today, we decided to highlight a topic that is slightly outside the usual energy debates, yet deeply connected to the whole nuclear energy ecosystem. Nuclear medicine and radioisotope production. We believe that understanding this link is really essential because radioisotopes produced in reactors play a crucial role in modern healthcare, diagnostics, therapies, and also in industrial and research applications. On the screen, you can see the link and you can join to our community, and you are very welcome to join our community. Please don't hesitate to do this. Before we start, just a quick note of the format. Our speaker will take about 30-35 minutes to talk us through the fascinating world of radioisotopes. Then, during the talk, please feel free to write your questions in the chat. We will collect them as we go. After the presentation, we will have 15-20 minutes just to ask questions and answer to the questions. And so we can start. Today, we are joined by someone who truly stands at the crossroads of nuclear science and modern medicine. Dr. Riccardo Bevilacqua is not only a PhD in applied nuclear physics. He is one of the rare experts who can translate the complexity of radiation, physics, and reactor-based isotopes into clear, meaningful strategies for global healthcare. At Electa, he bridges science and technology, ensuring that radiation it's not just safe, but understood, and that innovation moves forward with a scientific integrity. Please meet the expert who turned nuclear physics into a language everyone can understand. Riccardo, over to you.
Thank you, Svetlana. Let me show
One second. Yeah.
Yes.
I need us to close. I'm really sorry. 1 second.
It's totally okay. It's not a webinar if we don't start with some uncertainty when it comes to technology.
Okay, it's done. Thank you very much for your patience.
Thank you, Svetlana, for the introduction, and welcome to this webinar. I will share some slides, and I hope you find them interesting, and I will suggest some questions you can ask to me during the presentation, but feel free to come up with questions that I didn't suggest. So share screen, share presentation, and here we go. So the crucial role of radioisotope in medicine, industry, and society. So the question is, what a bridge, a pacemaker, and a rover on planet Mars have in common? Well, you should know the answer. It's isotopes, or particularly radioisotopes. But then the question is, what the hell is an isotope? What is a radioisotope? Is this something natural? Is it artificial? How does this relate at all with nuclear energy, nuclear reactors? And which role do they play in today's world? So this is what we will talk about. And let's start from the egg. This is a Latin expression. It means from the very beginning to understand what an isotope is. And we need to think about the universe Lego box. Now, all the universe, for complex that can look like, all the universe is really made by a basic set of small Lego building blocks. These are called quarks. There are 6 quarks, 6 leptons, their respective antimatter, so other 6 antiquark and antileptons. And then you have some glue that are the force carriers that keep these pieces together. And then we have an additional piece, which is called the Higgs boson, and with just very few pieces, made up the entire observable universe. But in fact, everything that is around us, your body, the computer that you're using, the chair you're sitting on, is even simpler. It's made just of 2 quarks and 1 lepton with some glue, keeping them together. And this is called the standard model. Standard model, you see the representation on the right. So it is our Lego box with build reality. And the three pieces that are in the red box, so the quark up, the quark down, and the electron, they are what build every single atom that you have around yourself in this moment. So only 3 elementary building blocks. And if you compare to Shakespeare, it took like 26 letters to write all his literature work. And Mozart and Lady Gaga, they need to use 7 notes to build all that music. But physics, well, you need only this small set of standard model and only 3 actually to make everything that is around us. So let's talk about up, down, and the electron. Well, electrons are just electrons. You cannot divide them into other pieces, and they fly usually around the nucleus of an atom if you have this standard representation that you see there on the right. Protons and neutrons together, they form the nucleus of the atom, what is inside the atom, and each of them is made by 3 quarks, and they are very similar. A proton is made by 2 up and 1 down, and a neutron is made by 2 down and 1 up. And you build them together, you get an atom. But if you want to get a more complex atom, then you need to put many protons and neutrons together inside the nucleus. So a nucleus of an atom is made by a certain number of protons and neutrons. You start from the simpler one, hydrogen is just 1 proton. And then as you increase the size of the atom, you start to add in more protons and more neutrons. And there is an imbalance there. So usually it's like that. The heavier is an atom, the larger is an atom, the more neutrons you have. So you have an imbalance, more neutrons than protons in heavier atoms. What is interesting is that a chemical element as such is defined exclusively by the number of protons. So it's the number of protons that determine if something is iron or is nickel or is cobalt, not the number of neutrons. That is variable. And let's take an example. For example, a fancy isotope, which is called iridium. Iridium has 77 protons in its nucleus. So 77 is the number that defines iridium. Any atom in the universe that has 77 protons is iridium. However, the number of neutrons can really change, can go, it ranges from 87 neutrons to 128 neutrons. We have seen every possible iridium from 87 to 128 neutrons. So large variability. And I just listed a few of them here. So if you have 77 protons is iridium, okay, 140 neutrons, then is iridium 191. Now it's a little bit tricky. Iridium 191, it means that you need to take the 77 protons plus 140 neutrons, the total, we call it iridium 191. Okay, so when I say cobalt 60, what I mean is that is cobalt that have a certain number of protons fixed for all the cobalt, a certain number of neutrons, and the total amount to 60. And what is a radioisotope then? Because this is the definition of an isotope. An isotope is something that has the same number of protons and a variable number of neutrons. A radioisotope is something that is a short for a radioactive isotope. Radioactivity means that this nucleus of that atom has an excess of energy, but at some point will release this energy out in form of radiation. But if we want to look at a little bit better what that means, what is an excess of energy? Well, you can look at the pictures on the right. You have an internal structure. Now, these are cubic, but usually we represent spheric. Where neither is a density or probability, so it's impossible to present it with a picture. But there is an internal structure, so protons and neutrons structure in a certain way. Now you have some structures that are more stable, so they stay as they are and they don't change. And there are some other structures that are unstable. A structure is unstable at some point, like if you put something on top of something that is a loose equilibrium, at some point will fall down. And in this falling down, the energy levels change, and this energy has to go somewhere, is emitted out in the form of wave or particle, and that is the emission of radiation. So it's the internal structure, how these protons and neutrons with their quarks are inside a nucleus. This determines which radiation will be emitted or if no radiation is emitted. Emits radiation, radioactive isotope. For example, if you go back to iridium, well, iridium-191, that has very stable internal structure, is like that on planet Earth, and you wait 5 million years, you will still find that iridium-191. And the same 193, very stable. But if you take some other isotopes of iridium, for example, 192, that is an unstable isotope. That means that with a certain half-life, so after a certain time, in this case is 74 days, it emits some radiation. So it changes its internal structure and emits radiation. But if you look at iridium-196, this change happens after 52 seconds. And if you look at iridium-190, what is the number? It's called my camera, 166. That is even more unstable. It just takes 10 milliseconds to find another structure emitting radiation. And when find another structure can become stable or can still be unstable and then decay again and again and again. Now, why is iridium-192 interesting? Well, in fact, iridium-192, that has this structure that is unstable and that in an average time of around 2.5 months, 3 months, emits radiation, is a very, very, very smart isotope because the radiation that is emitting has the right intensity that can be used to treat cancer. It has also a very convenient half-life, like around 3 months, so you can produce it in a nuclear reactor, you can transport to the hospital, it's inserted in a machine, which is called an afterloader, and then I have a picture here, we'll show you a picture on the source, and then what you do is that you place this radioisotope, exactly on the tumor, and this is called brachytherapy because brachys is a Greek word that means something that is short or near to. So this is a therapy where you put an isotope very close to the cancer. So you transport the radioactive source very close to the cancer, on the cancer itself. The radiation is emitted, this internal structure of the isotope change, radiation is emitted and is killing the cancer. And just to show you how important this is, okay, the guy on the right is me, and the one that I'm holding in my hand, and you see the tip of that wire, that is a mock-up of how small it is, an actual iridium-192 source. It is not really a 192 source. I wouldn't be able to hold it in my hand, but it's a mock-up, but just as a dimension. But what is interesting is the picture on the left. You say, oh, why do we use radioactive isotopes and so on? If you look, this is a curve that shows the survival with relapse-free in patients with prostate cancer. Every man at a certain age eventually will get prostate cancer. And it shows, the orange curve and the yellow curve is if you get external beam radiotherapy, so standard radiotherapy, or if you add, and this is the yellow curve, and if you add brachytherapy, so if you use iridium-192, in this case, there are other types as well, of course, of brachytherapy, but if you use brachytherapy, so you put this small radioisotope on the cancer, then you have a jump in the number of people that survive. So such something so tiny, so little, and have such a big impact. I mean, that is real people that are here with us or not here with us, people and their families. And this is for prostate, but this is for cervical cancer. Cervical cancer is terrible. It's affecting so many women all around the world. And the curve on the left shows the difference in the survival as a function of time of patients that receive brachytherapy or don't receive brachytherapy. That gap is real people, and it's the isotope that makes the difference. And if you couple this with three-dimensional imaging, then that number increases even more. And that is so powerful for something so little. It's just due to the internal structure of the nucleus. It's a little bit fascinating, I would say, even more than a little bit fascinating. And now you will say, okay, but radioisotope is a little vague, quarks, what does that mean? And how do we produce this iridium-192? Well, iridium in general, everything with 77 protons, is very rare. You find like 5 times more rare than gold on planet Earth. So it's very rare material. And on planet Earth, actually is found very, very, very deep inside the planet, because when the Earth was formed, it just went down into it, bound to heavy elements, it went down deep in the planet, and we wouldn't be able to even to assess it. But luckily, there is a very thin layer covering all the planet in the Earth crust of iridium that is available for us to extract and to use. And if you want to have some question to ask me at the end of the presentation, well, I suggest you 2 questions that are very interesting, I think. The first one is, okay, but where does this layer of iridium comes from? And a little bit hint, it has to do with dinosaurs. And then the second question is that why there is no iridium 192 on planet Earth? Why do we need to produce it, start from another type of iridium? No dinosaurs involved there. So what is the difference between, the iridium 191, which is what you find in this layer in the Earth crust, and iridium 192? We know, we discussed it, neutrons, 1 neutron more. So if I have 191 that I extract from the Earth crust, and then I want to get iridium 192, which is the one that I can use to save life of people, I need to add a neutron. Now, it's easier to say, I just add a neutron. What does that mean? Well, to add a neutron, you need to have a neutron-rich environment. And then what you do, that 191 exposed to this neutron-rich environment eventually will plop in a neutron and will become iridium 192. Now, iridium 192 has an unstable structure, we said. So this unstable structure causes some pressures and dynamics inside the internal in the nucleus of the atom. And by this dynamics, at some point, a quark flips. A quark down becomes a quark up. You remember when something goes from a quark down to a quark up, you have now a proton, not a neutron. Now it's not 77, now it's 78. So it's not iridium anymore. What is that? It's platinum. So in fact, another funny thing is that you could take the iridium that is used to treat cancer, and after it decays, it becomes platinum. You can make jewels that save life. I think I will do this when I retire. I will start my own jewelry with platinum from brachytherapy. It'd be so cool. Anyway, let's not lose focus. So how does that radiation emitted from iridium then kill cancer? Well, what happened is that radiation is affecting the DNA of the cells. And when you break the DNA on the cells, you have multiple breaks, the cell is not able to repair itself. Now, when the cell gets one break, it would repair itself in the DNA, and go back to work normally. If it was a cancer cell, you don't want it to repair and to go back working, because this is what you want to get rid of. So you put this source very close to the tumor so that you have high intensities localized there, only on the cancer cells, and then you have multiple breaks in the DNA, and then you cause the destruction of the cancer cell. But let's go back a little bit. Where do we get that neutron? With all this killing the cancer, delivering radiation therapy, we need to add that neutron. And to add that neutron, we have a series of neutron-rich environments where we can go to do that. One place is a galaxy far, far away, like Star Wars. So in the exploding of a supernova, that is a very neutron-rich environment, a lot of neutrons, and where all heavier elements are created, or can be the violent merging of neutron stars very far in the universe. Maybe there's lonely and slow death of a smaller star and so on. These are very neutron-rich environments, but it's not that convenient. It's not that I say, oh, I have iridium 191. Now let me go take the space shuttle and fly to an exploding supernova so I can irradiate that and add the neutron that I need. So I need to have something on planet Earth. And there are essentially two big ways to add a neutron to something, to create a new radioisotope that you can use. a nuclear reactor or a particle accelerator coupled to a spallation source. Now, neutron spallation sources are not many around, and they are built for other purposes, and they are not as efficient as a nuclear reactor. A nuclear reactor is the perfect environment. You have a lot of neutrons flying around. Neutrons are part of the process for production of electricity, but also for other type of research. And you can use this neutron-rich environment to put your iridium-191 and get your additional neutron that you need for providing cancer therapy. So there are really different types of nuclear reactors that you can use. And there are dedicated research reactors and reactors that are dedicated for isotope production. So there are some nuclear reactors that are built on purpose to produce these radioisotopes, to have this neutron-rich environment where you add neutrons to a material to make it radioactive so that you can use it in medical or industrial applications. But you can also use a power reactor, so a nuclear power plant, that can be equipped with a special channel in the reactor where you can place your isotopes. So you run a nuclear power plant, and then you place some material inside the reactor so that absorb the neutrons, you change its internal structure, and you can use it for your applications. And then there is the third type. This is very smart. There are some type of reactors that actually you don't need to make something special to add a channel where you would put your chemical elements to create isotopes, but actually you use components that you would already have in the reactor, and in that components, you dismantle them at the end of life, and we reuse essentially spent nuclear waste. You reuse it with a second life. Instead of depositing somewhere, you use it to cure people or to have other applications. And if you look on the website of the International Atomic Energy Agency, there is actually an interactive map where you can check how many nuclear reactors are currently operated in the world. There are 228 research reactors, so non-nuclear power plants. These are research reactors that don't produce electricity. They're used for other scopes. 81 of those reactors are actually for isotope production. So 81 reactors in the world, and there are 10 under construction and 6 that are planned. So it's expanding, and it's a very large fleet, and is distributed uniformly, more or less uniformly, through the globe. And I will take you a couple of examples of this type of reactors. One very nice reactor is this high flux isotope reactor at Oak Ridge in United States. This has a beryllium reflector, light water cooled, whatever that means, just the type of reactor that you have. And here they produced mainly three isotopes: iridium-192 that we talk about. I talk about application in medicine, but another application for iridium-192 is industrial radiography. I show a picture of the bridge in the beginning of the presentation. Every time you build such a structure, you need to check the welding. How do you check the welding? You do radiography. But you cannot take a long cable and X-ray machine power with electricity plug. So what you have equipment with a radioactive source inside. In this case, you can use iridium-192 is a typical application. And then you go and you check the weldings. Bridges, or you build a ship, or you need to make an airplane or aerospace component. You can go and check the welding and the structure by iridium-192. The same, you can use other elements that are produced in this reactor, like selenium-75. 75, again, is the total number of protons plus neutrons. It's a radioactive isotope. And the same is ytterbium-169. Ytterbium is used for something called gamma densitometry. So you look at the density of a certain material to understand. You cannot look from outside. There's no way to do it. You can't take a component, take it to a hospital or the facility. So you bring the source there, the isotope, radioisotope there, and you check the density of any material that you need to test. In Europe as well, we have several reactors for isotope production. These are two main ones. One is in Petten in the Netherlands. This is a high flux tank type reactor, and they are providing medical supply of medical isotopes. Particularly, something is called molybdenum 99, which then will produce technetium 99 metastable. I will talk about that. And other isotopes are iridium, iodine 131, lutetium, again, our hero, iridium 192. And there is a reactor in Belgium as well, BR2, that is also producing radioisotopes that are used in medicine and in the industry. And actually, in the Netherlands, they are currently building a new reactor will be called Pallas, with a very high, strong capability for production of radioisotopes for medicine. It's very, very important to have this availability because if you look at one specific radioisotope, it's molybdenum 99. This is the diagnostic workhorse, we call it. So molybdenum is produced in a reactor the same way. You add neutrons and you get this isotope with unstable internal structure, has an half-life of around 3 days. But it's not molybdenum, the one that you use in nuclear medicine to do diagnostic. What you use for that is technetium. So what happens is that technetium has a half-life of only 6 hours. So you don't have time to produce technetium in the nuclear reactor, drive it all the way to the hospital, take it to the pharmaceutical department of the hospital, bind it to the medicine, go to the patients are in line, you have many patients during the day, do the treatment and so on. It's impossible. So what you do, you use some device and some smart system that is represented on the right, and this has a funny name, that is not a holy cow, it is a moly cow. Moly cow. I'll tell you why. Because what you do is that you produce molybdenum 99 in the nuclear reactor. That has a half-life of 3 days. So it means that after 6 days, you have around 25%. So it lasts for a week. You drive this from the reactor to the hospital in this container. Now, in this container, molybdenum decays all the time, and it decays into technetium. So it changes structure and become technetium. Also, technetium will change structure, emitting radiation at some point after 6 hours. So every day, every morning in the hospital, they milk, and this is why it's called a moly cow, they milk by chemical separation out the technetium that was formed in the previous 24 hours inside the container. They milk it out, they use it for the patients. Morning after, they milk it out again, and so on. So the moly cow lasts a week, and you can have this constant supply. And if you think about the volume of this is huge. Like 85% of all nuclear medicine procedures worldwide are actually using technetium-99 metastable. 17 million diagnostic procedures per year. 17 million. There's a huge number that is done by this procedure. Any person with, all of us either been affected by cancer or have someone in our family that have been affected by cancer. Most likely, it's not the first time that you hear about nuclear medicine and technetium-99. There's a huge impact on global healthcare. But if you think for a moment that technetium-99 metastable with 17 million annual diagnostic procedures is impactful, wait to meet cobalt-60. So if I say cobalt, what do you think? Usually when I have these live sessions, I ask the people, if I say cobalt, what do you think? And everyone raise hands and say different ideas. But what you need to think about, if I say cobalt in general, is batteries. Now, 43% of global mining of cobalt ends up in electric cars. Other 30% ends up in your mobile telephone and portable computers. And then the remaining fraction ends up in the industry, aerospace industry, and so on. So cobalt is batteries in general. And if you look at the value, like batteries applications contribute 94% of the yearly growth in demand for cobalt. And the industry is skyrocketing, the more green economy and battery-driven equipment and so on, mining and demand is increasing for cobalt. But this is cobalt, we talk about radioisotopes, so a specific isotope of cobalt, which is cobalt 60. So how about cobalt 60? Well, this has a long history. Cobalt 60 was discovered in California by these two guys, Seaborg and Livinghood, and they discovered a lot of radioisotopes. That was the holy moly cow time of nuclear physics. We're discovering new radioisotopes every week or so. And in 1938, we've been producing the first cobalt 60. And then Seaborg, together with another guy, Macmillan, they went on discovering stuff. They discovered even plutonium. They got the Nobel Prize in Chemistry in 1951. Sadly, no Nobel Prize for John Livinghood. Even he would deserve it because cobalt 60 had such a big impact. I will show you how. And then the cobalt era started when they start producing cobalt 60 in nuclear reactors. For example, one most famous example is the Chalk River research reactor in Canada. And they start using cobalt 60 for treatment of cancer. And I don't know who chose the name, the atom bomb for a cancer therapy machine. Maybe it was other times. Now wouldn't be so popular as a name, but it was a big thing, They delivered the atom bomb that saved lives. And Sylvia Fedoruk, she was actually pioneering this, and it was a very interesting person. If you have occasion to read about her biography, it was a super interesting person, such impactful on global healthcare. But it is from the 60s that actually the main application of cobalt 60 started to be developing and became prevalent, and it is sterilization of single-use medical devices. So just, you remember 17 million treatments with molybdenum and technetium? Just in United States, not globally, just in the United States, 16 billion single-use medical devices are sterilized every year with cobalt 60. 30 to 40% of all single-use medical devices globally are sterilized with cobalt 60. This is the single most impactful radioisotope on healthcare in the world. There is nothing else that has such an impact because sterilization, 30 to 40% of sterilization depends on cobalt 60. It's incredible. And cobalt 60, you produce in nuclear reactors. So nuclear reactors, one thinks about electricity and other things. Nuclear reactors are what is providing 30 to 40% of sterilization single-use medical devices in the world. Imagine without sterilization. And there are around 200 facilities that provide this irradiation around the world. And as I said, can you really imagine a world without sterilization? Anyone ask me, but what do you think about nuclear reactors? And the right answer is, can you imagine a world without sterilization where we would be? And but you don't sterilize just single-use medical devices. You sterilize also implants, stents, human tissue graft. You sterilize food that is used for patients with a compromised immune system, but also preservation of food and control of crops from pests. In fact, that is Rafael Mariano Grossi, the head of the IAEA, and he released last year, IAEA released last year, a report. It's called Atoms for Food. And what we talk is how isotopes are contributing to the fight against hunger and sustainability in the world. You can find it on IAEA website. Super interesting reading. But cobalt 60 has also some other extraordinary applications. For example, you can land the Soyuz with cobalt 60. That sounds a bit incredible. But there is a problem. When we were landing the Soyuz, they didn't know how to make it to land without crashing. The parachute was not enough. And so they said we need to fire the backfiring engines just 80 centimeters from the ground. We need to turn on so that they could stop the fall and have a soft landing. But how do you measure 80 centimeters when you fall up from the sky, So you need to have a system that detects very precisely the position. And so you have a cobalt 60 source in the bottom of the Soyuz. You can see it indicated there on the right. And when that cobalt change internal structure is always this quarks changing, if quark flips, and this quark flipping emits some radiation, hit the ground, go back, and they can exactly measure. It said, yes, we are at 80 centimeters from the ground, backfiring engines, happy cosmonauts and happy astronauts back on Earth. Incredible. Did you know that? I don't think so. That's a super interesting thing. No, Svetlana said she didn't know that. Okay, maybe in the chat you can tell us how many knew about this. And but now another question: what do neurosurgery and rocket science have in common? You know, sometimes you say, "Oh, this is not brain surgery, brain radiosurgery. Yeah, this is not rocket science." Well, rocket science and brain surgery meet, and where do they meet? Surprise, on cobalt 60. Incredible, right? And the system that applies that is called the gamma knife. And I'm very excited about this because this is what I work with. And I have actually a Lego model of the gamma knife. So it's easier to explain it like this. So this is the system. Here I have a Mr. Patient or lady patient, I don't know. And this is the radiation unit. So inside here, you place an array of cobalt 60 sources. And these cobalt 60 sources, they're all focused to deliver their energy in one single point with the precision that is smaller than a millimeter, a sub-millimeter precision. And then you can perform radiosurgery to the brain, like brain surgery without any bisturi, without any cutting, anything, just using, again, I showed you the quark in the beginning, the quark down flips into a quark up. That flip of a quark in that structure can give you brain surgery. Like it looks like Star Wars to me or Star Trek. I'm still amazed with this by myself. But let me go back to the presentation. Here we go. So the gamma knife is the application where you have like rocket science meets brain surgery. And I show you the Lego model, but here is something a little bit more scientific. So you see this array of radiation from the change from this flipping of quarks. It's really meeting in one point, and we have around 360 machines worldwide, and 2 million patients were treated with this machine. And if you wonder about dimensions, this is also interesting. This is my old iPhone 12 mini, so it's a smaller one. Now my daughter has it. And then you can see the size of the actual pellets that we have inside the gamma knife, but I can also show them live. Yes, so it is like this. So this is around 20 grams. Can I put it in focus? 20 grams of cobalt. This is not cobalt 60. This didn't go in the nuclear reactor yet. So this you put in the nuclear reactor, become cobalt 60 because you add the neutron, and then only 20 grams. You know how much cobalt you have in an electric car? 14 kilograms. So one electric car, 14 kilograms of cobalt. One telephone is around 10, 20 grams of cobalt from the batteries. But if you add one neutron, you change the internal structure, and then that same 20 grams that last few hours in an electric car, 14 kilograms, only 20 grams, you can have brain radiosurgery for 5 years. So this is worth 5 years of brain radiosurgery. That's really the power of nuclear physics. And there is nothing else, there is no other technology in the world that can put so much power in something so little. And you do this in a nuclear reactor, you have a neutron-rich environment, or you can do it in the explosion of a supernova. But yes, we don't have the technology to reach a supernova to do that yet. Okay, let me go back to the presentation because I wanted to show you another couple of things. And this is interesting because I said you put this in a nuclear reactor, but how do you produce cobalt-60 in a nuclear reactor? Well, this is a very interesting way to do it. And to teach you that, to tell you about that, I need to say something about how you control a nuclear reactor. Now, you control a nuclear reactor by keeping an equilibrium in the number of neutrons that are emitted and the number of neutrons that are absorbed. And how you keep this equilibrium? Well, you have the fuel like uranium or so, emitting neutron, absorbing neutron, breaking up energy, warm up the water, steam, turbine, electricity at home. Or you put cobalt inside and so on. But to control this equilibrium, you need to have something that regulates the flux of neutrons, which you have all the time. So you put some rods, some bars, and these adjuster rods or control rods, they are made of some neutron-absorbing material. And the more you push them inside the reactor, the more neutrons are absorbed. You take them out, less neutrons are absorbed. So you control the reaction like this. And you know, when Enrico Fermi built the first nuclear reactor in Chicago under a basketball field, I think in the middle of the city, he was like having people, he was making the calculations with pen and paper. Oh, I need 20 newtons more. I'm not kidding. Someone was manually pushing these rods inside and outside the reactor. And he also had a guy standing on top of the nuclear reactor with a large bar that was going to shut down the reactor, absorbing all the neutrons. And this guy had this bar attached to a rope, and the guy has an axe in his hand. And when Fermi was saying, we need to shut down the reactor, the guy was supposed to cut the rope with an axe, and the control rod was falling down, absorbing all the neutrons. The neutrons turn off the reactor. So that guy was called the Safety Control Rod Axe Man, which the acronym is SCRAM. And still in every nuclear reactor in the world, there is a button, which is called SCRAM. Now there is no guy anymore with the axe cutting the rope, but still you push that button, all the rods go inside and shut down the reactor. Now you say, okay, Ricardo, but all this, how is this related to cobalt production? I come to that. Let me come to that. So the fact is that you need to have a neutron-absorbing material to control the reactor. And on the other side, I want cobalt-59 to absorb 1 neutron in order to become cobalt-60 that I use for sterilization and gamma knife, brain radiosurgery, and so on. Why not to put the two things together? So the control rods of a type of reactor that is called CANDU nuclear reactors, very popular Canadian design of nuclear reactors. The control rods, instead of having them on another material that absorbs neutrons, they fill the control rods of these small pellets that I've been showing you. And that pellets, in the times of operation of the reactor, absorb the function of absorbing the neutrons, absorbing the neutrons and controlling the reactor. When it's time to change the bar, you don't throw it away as radioactive material waste. They pour out the pellets, they ship to a manufacturer, where they are put inside capsules, and then they are reused for performing brain radiosurgery. So full sustainability. That people don't know. You know, they think, oh, how you do that? You produce green electricity, clean electricity from nuclear energy, and then the waste is not waste. You recycle it and you use it for other applications or industrial radiography or sterilization. And that is, I think, fantastic. So in conclusion of this presentation, and then you can ask me some questions, hopefully, or I suggested a few, like about iridium, what has to do with dinosaurs. So in general, with no isotopes, we couldn't build any bridge because we cannot check, you know, these big bridges like the Öresund Bridge here in Sweden, between Sweden and Denmark, or any large construction. You cannot build any airplane, flying any airplane. You know, the Boeing it was Airbus had a recent problem with cosmic rays. They need to test electronics from cosmic rays, and they do it with sources from reactors. 30 to 40% of all single-use medical devices worldwide. That I think is, that by itself, you know, I don't need to say anything else. Imagine to get rid of 40% of single-use medical devices. And this number was even higher during COVID time when you needed to sterilize more. And if you think about the holy cow, moly cow, then 17 million diagnostic procedures every year with technetium, again, nuclear reactors. And I show you the example in the beginning with brachytherapy, the difference that it makes in treating. I just showed two examples, cervical cancer and prostate cancer, but there are many other indications. That difference in the curves from one curve to the other, that's not just numbers, that is lives of people. That gap of having or not having brachytherapy with iridium-192, that is really lives of people, our lives, lives of our parents, our children. our friends, the people that we love. That is huge. That is huge difference. And it's just because you can add a neutron and change the internal structure of the nucleus. That's to me is amazing. So yeah, if I can ask a question to you, it would be, can you truly imagine a world where nuclear technologies and radioisotopes are not powering really our progress in medicine, safety, and engineering? Can you?
I guess no. After your fascinating talk, I can't imagine it. Actually, just a lot of stuff new for me. And I would like to ask you actually about where does this iridium layer and what about stuff with dinosaurs? They knew about iridium. They met some kind of iridium.
It's a sad story for the dinosaurs, but it's a happy story for humanity. And let me share again. So I have hopefully a slide on this. No, my slides crashed, but let me try again like this. Stop share, and then share again. The dinosaurs don't want to be shown here. Here we go. Okay. So most of iridium is found on deep in the planet. So you know how the planet was formed, like some supernova exploded somewhere in the universe. Many supernovas, materials, every chemical element was thrown around the universe. At some point, dust start accumulating in a certain area, a local accumulation disk or nebula, whatever, and then we start to get close to each other, and then the more and more dense, and then the sun and the solar system was formed. So we are everything, planet and our bodies and everything, we are just stardust. Every single atom that is not hydrogen came from in the core of a star that is not there anymore. But the iridium somehow collapsed inside the center of the Earth. But then there is a very fine layer of iridium. So how did this arrive on Earth? It should have arrived later. It was not there from the beginning. When Earth was formed, that iridium is inaccessible. This layer is like when you make a cake and then you put sugar on top of it, you have a layer on top. So what does that come from? Well, it came with an asteroid. When you do a chemical analysis of asteroids, you find that they are much richer in iridium than what we see on Earth crust.
It's
And we could date, geological eras. You can date when a certain layer in the crust was formed, and they have been able to link this to one specific event of a very big asteroid, the biggest asteroid that ever came on planet Earth. Looks like a Hollywood movie. And this asteroid arrived and created this nuclear winter and dust over all the atmosphere in the planet, and all large animals like dinosaurs died and so on 66 million years ago. Well, that cloud was made of the dust from the disintegrated asteroid, and when it settled down on the planet uniformly, formed this iridium layer. So it's very sorry to say, but you cannot say that the formation that the iridium on Earth didn't cause any harm to dinosaurs. So it's really thanks God. We have to thank the dinosaurs. When you see that gap on the people that you are treating with iridium, or with all the industrial radiography that you do it, and someone asked me, oh, but what is the price to pay? Well, it was not us paying the price. It was the dinosaurs paying the price for us. So thank you, dinosaurs.
Thank you. Yes, it means that we have only few small sources for iridium, and it's the reason why we should produce iridium. Am I right? Or
Yeah, so iridium that we find on planet, on the crust, is iridium 191 and iridium 193, which are iridium that is very stable. That means that it doesn't emit radiation, but you can mine it and has several applications. If you want to get the iridium 192, that is the radioactive one that we use in the applications we discussed, then you need to activate it in a reactor by adding a neutron. So you need to mine it, and then you need it to put it in a reactor. And the other question that I was suggesting to ask, but I can answer now, is why don't we have iridium 92 already on the planet? Why do I need to add a neutron in a nuclear reactor? Well, because the half-life, we said, is around 2.5 months, 3 months. So that iridium that was created as any other chemical element in a star, either in the core of a star until iron, or in a supernova explosion, anything heavier than iron, like iridium, that has been created billions of years ago, traveling through the universe. By the time it arrived on Earth and it formed our planet, it was long decayed. That went all the quarks flipped, so to give a stable structure. This is why you don't have anything radioactive left when it comes to iridium, because it's too short life. So we need to reactivate it again. So someone tell me, oh, but this is artificial or natural? It's very natural because it was there from the beginning. We just need to reactivate it in order to use it, to recharge the battery, if you want to make that.
Yeah. Ricardo, we have one question. Could you just
let's see if I know the answer.
check Q&A?
So,
Can you see it?
yes. So, that is I think is a provocative question. I can read it, but I'm not sure if I can answer it. It says, as a nuclear physicist, apparently, facing the problem, how to explain that at CERN we don't produce an atomic bomb? I hope no one thinks that CERN is producing atomic bombs. And what do you think that the most common misconception society holds about radioisotopes? Okay, this I can say. And how can you address them through communication strategies? Good question, actually. In the beginning, as a nuclear bomb, I thought, no, I don't. So, of course, CERN doesn't produce nuclear bombs because it's, to CERN is a research facility, right? A research facility that has mostly accelerators and accelerating rings. And it's like to say why a factory that produces toys is not producing the space shuttle. The fact that they produce something, it doesn't mean that it produces the same thing. It's totally different industries. I don't even know from which point to start. CERN is really like more of a university laboratory. There's nothing to do, doesn't have the capability, not the competence, not the materials, has nothing to do with that. But I think the most common misconception about radioisotopes is that people think that they are not related to our everyday life. If you ask to someone and say, did you ever benefit from a radioisotope in your life? Me? No. And I ask, did you get the vaccination when you got when it was COVID time? Or did you get the vaccine when you were a child? Or did you ever go to the doctor and they put on some sterile gloves? Yes. 40% of that was sterilized with cobalt-60. Did you ever cross a bridge with your car, or did you ever take an airplane, or did you ever eat some fruit that comes from some country that would get rotten before reaching here, or did you ever drink coffee? There's a process called monsooning of coffee, which is done also accelerated using irradiation from isotopes. Isotopes are really everywhere around us. All our life is determined by that, just that we don't know. So what we need to do is what we are trying to do here today is really to make explicit what is the contribution of isotopes. Because otherwise we risk that someone will say, isotopes, what's that? No one uses them. And then, our capability of having access to them will decline. Thanks God, the world knows. And this is why you've seen there are a lot of research reactors producing isotopes. There are new projects like Pallas here in Europe or other projects around the world. So thanks to God, the world knows, but we need to talk more about that.
Thank you very much. It's really new something for me, and I guess for some people who actually is not into the physics. Hello, everyone again. Could someone ask, or maybe some would like to ask something about isotopes? We have 6 minutes
I can
before.
tell you where to find the isotopes if you want to play with your children. You can make your own nuclear laboratory at home. So there is something that is called low sodium diet. Some people have a low sodium diet. And you can go to your local supermarket and buy low sodium salt. But now, if something is low in something, it needs to be high in something else. Like low sodium salt, it means that your salt, table salt, is sodium chloride, NaCl. If it is low sodium, it means that we need to compensate for something else. Otherwise, instead of 100 grams, you get 70 grams, 70 grams. So you buy 100 grams, what is the remaining 30, 40%? It's potassium. So we put KCl, potassium chloride, instead of sodium. And potassium distributes, has a certain distribution of isotopes, and one isotope of potassium is potassium 40, which is naturally radioactive. So it comes from that supernova explosion, has a very long half-life, so it's still here on the planet. So if you take a box of table salt with low sodium from the supermarket, and you take a radiation detector, and I did it, I have a video on LinkedIn about that if you want to see it, and you measure that radiation, that is 5 times higher than the background.
Really?
Yes. So you can actually, and there is, since it is called a norm is a naturally occurring radioactive material, then the regulations are very different with regulation in the nuclear industry and so on. That means that you can sell that at the supermarket,
Yeah.
and you can buy it. And sometimes I have friends over dinner at home and said, "You want some radioactive pasta?" And then we use the low sodium salt. And it's also interesting because if we would tell to people that, oh, look, this material here, that is 5 times higher than the background, it's scary, you know? But
Yeah.
then you go to supermarket and you buy the salt. You can stay, a couple of hours with the 2 kilograms of salt around your jaw will be the same radiation dose that you get when you get a dental X-ray. And the other place where you can experience a nuclear physics laboratory, even though there are no radioisotopes there, is if you take an airplane because of cosmic rays. So you can do your own small nuclear physics measurements on an airplane, maybe with your salt, your table salt. And when
Yeah,
very
exactly.
dangerous nuclear physicist, yes.
Could you just check Q&A again, please, Ricardo?
There is someone saying that, of course, it was a joke about the
Yeah.
CERN thing.
Thanks you. Thank you very, very much for your great talk, fascinating talk. Uh, okay, I didn't just done with this question. Thank you very much. It was great. It was really a pleasure just to have this time with you and to hear from you about so fascinating topic about isotopes, how they help and support our lives. Actually, it's not that obvious stuff for a lot of people. And it would be great if some of you guys can follow up our link that I showed you before, and you can just watch this video again and maybe to text some questions to Ricardo directly, and maybe we can create in the future something new, a new video based on your questions, on your interest to this topic. And thank you very much again. It was great. Thank you for your time, and thank you for your time, Ricardo. Thank you for the great talk.